We'll now continue to visualize this W matrix. The W matrix is an n by n complex matrix. Each of these elements have amplitude 1 but different phase. There's a negative sign here as defined by this equation we have. So if we plug in different k's and different n, so k's is going down the rows and n is going across the columns from 0 to n minus 1. Let's plug in, and if we are going to represent w as e minus j 2 pi over n, then you'll realize that as we change, as we substitute different k's and n, we can see it in this form. So W0 basically means we are substituting W as e minus j 2 pi over n, and we are substituting different values. We just call it n, so there's no more k and n here because we collapse them together. Now you can see then very clearly that this matrix has this kind of elements, and it is very special because it is actually also symmetrical. Okay. Additionally, I hope that when you look at the W matrix, you are going to study it from the perspective of how each row is behaving, because as you saw in the last slide, it is to get this element, let's say the x1 element, we are multiplying this row vector with this column. Therefore, it is how this row is behaving with respect to this column that is producing x1. Now, we look at the first row, and it goes from x0, 1, 2, 3. And basically, what it is, now I'm going to plot for you. First, I'll show you the element from this notation, and I will now give you the values at each of these element. And you will see that actually the magnitude is 1 for everybody, and the phase is going from 0 times pi over 4 radian to 1 times pi over 4, 2 times pi over 4 with a negative sign in front. And as you know by now, this is a rotating phasor. Let's go and work out why is this so. Let's substitute here capital N equals to 8, because this is what we are playing with in this matrix. Minus 2 pi over 8. And here we are talking about k equals to 1 here. The k equals 1 row of W. And therefore this is minus pi over 4. And now we are modifying by little n equals to 0 to n minus 1. So this guy goes from 0 to n minus 1. So therefore that's why we have all these elements of, and we're seeing n is varying across each element in this row vector. And of course, when you plot this, how does it look like? So I will show it in a different way now. In the diagram below, this is the corresponding phase diagram of each of the element. And what am I drawing here? I'm drawing the unit circle. The horizontal axis is the real axis. This is the imaginary. And of course, this is number 1. And here is minus 1. And here is j. And here is minus j. And if I'm drawing for you, let's say, an arrow like this, then this is magnitude 1, angle 0. So you see that the first row is all magnitude 1, angle 0. The second one is a phasor that is rotating what? Rotating clockwise. And at each step is rotating by pi over 4. Because you see here is 0 degrees. Here is clockwise by minus pi over 4. The second step, another minus pi over 4. So where do we see this? We see this here. The first element, angle 0. The second element, minus pi over 4. The third element, minus pi over 4 times 2, which is minus pi over 2, and so on and so forth. So you can see visually that the phasor is rotating clockwise at each step by pi over 4. Now, I'm going to ask you this question, so pay attention. If I want you to draw W87N, then of course you are going to put here the same minus pi over 4, because this is what? This is 2 pi over n. 2 pi over n is equals to pi over 8. Pi over 8, sorry, pi over 4 here. So pi over 4 is here. Here we have k equals to 7, n equals to 0. So we are substituting these values here to produce this guy. So if you compare the coefficient, the first one is 0, second one is 7, 14, 21. So can you see? 0, 7, 14, 21, and so on. Now, it's actually very instructive for us to convert it into positive angle. Here is we have negative angle. Negative angle goes down. Remember? Here is, let's say, theta. Negative theta. We can also reach this point by saying it's 2 pi minus theta. So you realize that minus 7 pi over 4 is the same as plus pi over 4. Because, let's see where is minus 7 pi over 4. This is minus 7 pi over 4. This is pi over 4, because when they add together, you get 2 pi. So we can convert a negative angle to a positive angle. And when you convert for each of these elements, then something very strange happens. You'll see that, hey, isn't this very, very similar to W81N compared to W87N? There is a small difference. What is the difference? Here, he is rotating anti-clockwise by each step, as compared to the first element, sorry, k equals to 1 element, where he is rotating clockwise at every step. So you compare this red bar, red box, with the blue box, and you'll see that actually they are the same frequency. The difference is that they are rotating at the opposite direction. And in fact, it is exactly because of this. In fact, every element is complex conjugate of each other. And that is why later on you'll realize that when we are trying to get a real number, we are always adding the complex conjugate factors of W together. Okay, this is quite deep, and it shows you why, for example, let's remember this. Ej theta equals to cos theta plus j sine theta. E minus j theta equals to cos theta minus j sine theta. This guy and this guy are complex conjugate each other in rectangular form. In the polar form, there's a minus sign here. When we add some numbers with its complex conjugate, out comes only the real value. Okay, and this is why in our previous example, we're adding, if you go through our examples before, we're adding this guy with his complex conjugate to get the cosine. This guy plus this guy, complex conjugate, to get the cosine at different frequency. So with that, in the next slide, we'll show you one final example of how to calculate DFT. Thank you.